Great, thank you. Yes, my name is Lisa. I'm at the German Weather Service. I promised lightning. I'm actually going to not deliver that. I'm going to actually just focus this talk on assimilation of Nowcast objects or objects only in the interest of time. Just want to clear that up. But maybe I can give a teaser of the lightning information at the end. So just to put my work into context, I don't want to go too much into the details of convective data assimilation at the German Weather Service. But the work that I'm doing is part of the Symphony project, which is almost completed project to develop a rapid update cycling at the German Weather Service, which should be the first version of it should go operational fairly soon. It's currently still pre-operational. But just the basic idea of it is that it's a local ensemble transform Kalman filter. And so we cycle data once an hour. Several ways it's an improvement of the previous system, but one way that it's an improvement is that we are attempting to bring in more observations of convection and precipitation. So two types of observations that are already running are, of course, 3D radar scans and infrared and visual wavelengths from the Severi instrument. And then what I'm working on, which is still in progress, is lightning flash rates and objects. So what on earth is objects? Before I explain that, I just wanted to give an example of what convective scale data assimilation looks like sort of in our system and in Germany at large. So I just pulled an example from last August of a convective system or a series of convective systems altogether. This is a snapshot. The top left plot, you can see the observed radar composite. And so what you can see is different convective cells sweeping over the area together. And if you look on the plot below that, it's the first guess, so the forecast at that time, just preceding the data assimilation. And so, of course, what you can see is, yeah, on a 100-kilometer scale, it does get the overall system, the overall precipitation right, but what it doesn't really get right is where the convective centers are. So the challenge is not really to update a continuous field, but to update sort of these coherent objects moving through space and time. But the way we do that, of course, is by updating a continuous field, namely the model variables. So what I've shown in the second column is the increment. If you now assimilate this radar picture or the three-dimensional radar data that this picture comes from into the model to bring these two together, the second column shows you the temperature and relative humidity increments or water vapor increments that you would get from the LETKF. And it makes a lot of sense, of course, right in the center of the picture, you're missing convection. And so what the model is doing is warming in that area and then also adding water vapor in some places and taking it out in others. Another thing to notice about this is that the temperature increment tends to be sort of large scale and smoother, and the water vapor increment or the hydrometeor increments are more localized and point-like. But where does this get us? You can ask now, when we make this adjustment, do we actually correct the convection in the model? Because what we're doing is changing the state in order to turn on a process. So this is what the same spot looks like 20 minutes later. The top plot shows the observation. So you can see how the system has developed from the top left plot. The second plot in the third column shows what the forecast would look like if we did no data assimilation. So it's basically that bottom left picture moved forward in time in the model. And then the bottom picture is what it looks like when we assimilate radar data. And so you can see, yeah, it is in fact clearly closer to the observations. The intensities of these particular cells are too strong at spots. And we also don't really have the convective centers still, the coherence of the objects the way it is in the observations. You can also ask yourself, how long is this going to last in time? So I've shown these, the observations and then these two types of forecasts at 60 minutes. So the first column is 20 minutes after the update. The second column is 60 minutes after the update. And here it's, legitimately more difficult to tell what's the difference between the no assimilation case and the assimilation case. And some of you probably have ideas for how you would measure whether the assimilation case is closer or the no assimilation case is closer. Typically, what we do is use some sort of forecast score to measure that. And what I've shown here is the fraction skill score. So the fraction skill score is a handy score because basically what we do is you take, you apply a threshold to your data. In this case, we could apply a threshold to the reflectivity that we see. And then you superimpose a regular grid. And for every box on the grid, you compute the fraction of points in the neighborhood of that box that exceed that threshold. And if you do that for every point, with an overlapping box, and for your observations and the model, you can look at the difference of this in time and average it over the whole field. And if you look at the deviation of this from some no-skill case, you can get this unitless number that is best when it's 1 and worst when it's 0. And that's what I've plotted here. So those 3 cases, well, 2 of the cases that I showed, so the no assimilation case and then the radar assimilation case. And just for fun, I've added a case where I assimilated conventional observations only. So that's radio sounds, aircraft, etc. And you can see this is, if you think of the FSS as a measure of how good is the convection that we get, you can see that it's hugely better when we assimilate the radar data. So what I showed here, it does make a difference, and that difference does last for some time. So I've shown 2 hours of forecast here, and it's still markedly better than the no VA case. Okay, so what's interesting about the fraction skill score is that it considers how close we get to the observations at a certain threshold and at a certain spatial scale. So if you're interested in systems of a high dBz, you can look at that and see if you do well in that regard as opposed to low intensity systems. So this brings me to the idea of what we assimilate and call objects. Basically, we take this F, this fraction, we're going to call it texture fraction. I'll mention that again later. And we use that as an assimilation quantity. So we take a threshold and we decide that any convective object is the polygon where that threshold is exceeded. So a threshold in the dBz. Then we define a neighborhood box for this gridding to give us a spatial scale. Then we do the same thing for observations and model, just like when we compute the FSS. And so this number, this F, we can, if we have an observation and we have 40 model equivalents, we can just feed that into the local ensemble transform Raman filter and see what happens. The nice thing about ensemble filtering is, as long as you have both an observation and a model equivalent, the LATKF will eat the data, and you might get something sensible out. I think I've more or less explained that, so I'm going to skip that slide in the interest of time. So what does this look like? Again, we're basically taking the integrand of the fraction skill score, and we're computing it for observations and for models. So I've just taken 2 examples here of convective situations. The first row shows an isolated cell, just on the edge, actually, of the German radar network, that is in both the observations and the first guess. It just happens to be in the wrong place. And then what that looks like in terms of this texture fraction, if you plot the observations minus first guess of the texture fraction, you see a sort of dipole of negative values up here and positive values farther south, because it's reflecting the fact that this convective object, which has a fairly small spatial extent, is displaced in the first guess. You could also do this to a more complicated picture, like the one I had earlier, where the first guess convection is sort of in the right place, but its horizontal extent is completely different. And then you get a more complicated picture of observation minus first guess. But this is essentially, this third column is essentially the information that gets fed into the Kalman filter. And then the Kalman filter is left to interpret that in terms of how should the model variables change. And so what I want to show here is just how that data assimilation increment might change when we go from assimilation of three-dimensional radar scans. So that's really all the radar instruments across Germany scanning at different heights, and we reduce all of that down to this two-dimensional quantity called texture fraction. And what I've shown here is the increment in temperature, water vapor, and rain, so liquid water, between these two cases. So a case where we start off from the same first guess, but we assimilate these two different quantities. And you can see that it's fairly similar. But in the case of the texture fraction assimilation, we tend to preserve the warming part. That's in this case, in a case where we add convection into the model, and sort of do away with more edge areas, because these observations have less of an extent. So you can also look at vertical slices of this. In this case, I've also added increments in ice and graupel, just for fun. So these are, let me just quickly go back. If you take a horizontal line across each of these plots, and then plot a vertical profile at that horizontal line, you can see that the radar data, of course, which are three-dimensional, extend far more in space. And the texture fraction observations, they're kind of the meat of the sandwich, if you will. They take sort of the central part of that, but leave out the vertical extent of it. But you could see it does take it gives extra heft to what might be the most essential part of the observation. And here you might ask yourself, well, how did you decide at what height to put in the observations? The blue lines in these increment plots are actually the height of the observation, because the texture fraction observation is two-dimensional. And the answer is a little bit hand waving, a little bit of physical basis. So basically, we have this two-dimensional height, and we have to assign it to some vertical level. And what we've done as a sort of ansatz solution is we've taken the height of the second lowest scan of each radar station and taken the average of that height. And so whatever point, this is a map of Germany, if you see in the colors, whatever point you are, the height that you assign the observation is basically the average radar beam height. And that number distributes like this. It ranges from about 1,000 to about 8,000 meters. So it has a mean of about 4,500 meters. So for points where we don't have an observation, where we only have ensemble information, we just assign it this mean height. Okay, so the question is, what does our skill score look like when we actually assimilate the integrand of the skill score? So I've plotted that here. So again, as before, we have this no assimilation case. And of course, the skill drops off in time. We have the 3D radar DA case. That's the red line here. It's much better than no DA, of course. We could also just apply a 37 dBz threshold to radar and only use the strongest signals. That lands us somewhere between the red and the black. However, if we reinterpret that 37 dBz threshold as texture fraction, so it means we smear it in space, kind of, then we get actually higher scores than if we assimilate radar alone, which is kind of surprising and kind of exciting. Maybe I'll just skip that for now.
2 minutes.
2 minutes, okay. Let me just skip past that in the interest of time then too. So the next step would be to take that observation and apply it to this pre-operational rapid update cycle. What I've shown here is what we call the model clock. This sort of summarizes all the different forecast systems that the German Weather Service has. Absolutely nobody understands this graphic. 2 people on Earth understand this graphic. I'm not one of them. But basically, what you see is that we have this routine forecast. And at 3 UTC every day, we branch off from those initial conditions, and then we start this rapid update cycle where we assimilate once an hour with 2-moment microphysics. So it's a more sophisticated model version. It's more frequent assimilation, and it's a more complex radar operator. So it's a pretty good system. It's heavy. And the question is, if we now add the texture fraction to that, can we actually improve the convective forecasts? This was actually the wrong plot. Oh no. Let me just, shoot. Oh, the punchline is a little bit lost because I accidentally switched out this plot right before. But basically what you can see is that, well, you'll just have to trust me because it's the wrong plot. Maybe I'll replace it later for when the slides get stored. The improvement is slight. We have a slight improvement in the FSS when we add this fraction to it. So I'll just summarize, you'll have to trust me on the last plot. Basically, it is possible to assimilate the integrand of the fraction skill score. And what that gives us is a way to interpret convective objects in a gridded way for ensemble data assimilation. We have found through some tuning and a lot of testing that the assimilation of the texture fraction improves forecast scores on the scales where we define this quantity. And when we add it to the existing rapid update cycle system, it seems to add value. So this is exciting. I would like it to add more value than it currently does. So my work for the next few months is more tuning and more improvements of this assimilation. We are also working on assimilating not just the texture fraction, but extending the principle to assimilating features of convective objects that are produced by the operational Nowcast system. And in a very similar vein, we are working on assimilating lightning flash rate. I didn't have time to talk about that today, but I'm happy to answer questions about it, or if I'm happy to take emails about it also. I can send slides or whatever on that. And I'll close with that. So thank you.
Thank you. So we have 3 questions. First one is from Prashant. You want to know if the texture data assimilation helps to avoid assimilating correlated observations and present better performance.
I'm sorry, can you repeat the question? I didn't.
It's whether the texture data assimilation helps to avoid assimilating correlated observations.
It might be. It might be. I don't know. That's a good question. That it might improve it because it avoids that problem. It could be.
Okay, so a question from Tobias. It's how does the size of the neighborhood affect the assimilation results?
Oh, great. That I'm glad someone asked, then I can go back to another slide. So basically, the size of the neighborhood is not that important, but the way you define it will affect which scales you improve the score on. So I did some sensitivity tests where I defined texture fraction 4 different ways. The black and red here are low dBz thresholds, and this should say 37. The blue and green are high dBz thresholds, and then 2 different box sizes. So for example, the black line is a small neighborhood box, and the red line is a large neighborhood box. And then if you compare the fraction skill score computed at those scales, you can see the one with the small box gets the highest score. You do the FSS on the small box, and vice versa if you do the large box. And the same is true if you compare the top row and the lower row. The FSS for the higher dBz is best when you define texture fraction at higher dBz. So you can sort of choose which scales you want to improve based on how you define the texture fraction. And I should say here, the box is defined in terms of icon model pixels. So it would be this number times about 2.2 to get kilometers.
Okay, thank you. You have more questions. I think you can answer it in the YoPad because we have to get to the next presentation. Thank you, Lisa.
Thank you.